Thank you. And thank all the organizers to give me this opportunity to talk in this fascinating conference. I don't know how much I can contribute it, so I would restrict myself mainly for non-unital case and hope that there is a different angle and a complement for all these fascinating talks. So let me see, I can move it. But let me start with the unital C-star algebra. So T of A is a tracial state space, and there is a natural pairing, and that is in order preserving homomorphism from K0 to the real continuous affine functions on the tracial state space. So now I'm not going to really talk about that. Let's move ahead. So again, Z is a Jiangsu algebra, a unital separable infinite dimensional simple C-star algebra, which is an inductive limit of subhomogeneous C-star algebra, and has the same Elliott invariant as the complex field. As I mentioned before, you start with any unital separable C-star algebra, and as a group, the K theory doesn't change after tensor Z, and the tracial state space will be the same. And assume A has a weakly imperfect K0, then Elliott invariant will remain the same. So that is one of the reasons that we classify C-star algebra, which are Z stable, since Elliott invariant are not going to distinguish A from A tensor Z. Okay, let me mention this theorem, classification of unital simple C-star algebra. This is really, lots of people have this contribution to this, but let me summarize and slightly differently. Say I have three parts. First part is description of the invariant. So it basically says that only one restriction is on the K0. So K0 is always a countable weakly imperfect simple ordered group, and an element is positive if and only if the pairing give you positive element, strictly positive, of course. And I think this is predicted by George Eliot. It's a theorem of Gong, Jiangsu, and Michael Roden, I think. The second part is once you have the description of invariant, then you want every invariant to be hidden. So for any weakly imperfect Elliott invariant, this is a six-tuple. As I mentioned, that you don't really need a G0, but I put it here, emphasize this is because of one, okay? And then we'll see this actually somewhat you actually need it in later on. So delta is any metrizable short-wave simplex, any countable weakly imperforate simple ordered group, and any order preserving satisfy this condition, and rho of U is 1. And G1 is any countable abelian group. And then there exists a unital separable simple C-star algebra, A, which is the inductive limit of subhomogeneous C-star algebra and has, say, rationally generalized tracial rank at most 1. So that the Elliott invariant is precisely the precise subscribed to 1. So this is the range theorem. And the third part, so the second part is given by Elliott, and we have some refinement on this. Third part, I think I should move to next page since it doesn't fit here. I hope that I assume you can see the last end of the slides. So 2 C-star algebra in this class are isomorphic if and only if they have the same Elliott invariant. I'm not going to say the history about this, but just remind some names directly relate to the statement I just given here. And so the first part is Elliot, Gong Jiangsu, and Michael Rodin. The second part is Elliot and Gong Yu and myself. And there is isomorphism. For the third part, there is the isomorphism theorem. There is a reduction theorem. There is a theorem about quasi-diagonal traces. And since the way I stated, there is also a proof of Thom-Winter conjecture. But today, I'm not really going to talk about these. We talk about non-unit case. But why non-unit case? Well, indeed, that if you have a non-unit separable simple C-star algebra and assume the positive cone is not zero, and then you will have a projection in the matrices. And if you cut down the matrix by this projection, then you get a unit separable simple C-star algebra, which actually is stably isomorphic to A. So for those simple C-star algebra, the classification could be easily reduced to the unital case. But what is not perfect? There is a non-unital separable simple C-star algebra Z0, which is locally subhomogeneous and with a unique tracial state. And the K-theory as a group is the same as Z, but the pairing is a trivial. So the positive cone is zero, and Z0 is stably projectionless. If you start with any separable amenable simple C-star algebra, and you tensor with a Z0, and that's a Z-stable simple C-star algebra, and K0, the positive cone is zero. And A tensor Z0, therefore, is a stable projectionist. And you don't really change the K-theory as a group, and didn't change the trace. In other words, there are lots of these algebras which are stably projectionist. But these also can be classified, and you start with this classification theorem with Elliot, Gong, and Yu, and now it's published. So the class of KK contractible simple separable amenable C-stable C-star algebra is classifiable. It's classified by the invariant T tilde and sigma A, and any C-star algebra in the class is actually inductive limit of a Razak algebra, which I will not really describe today. So T tilde is a set of lower semi-continuous densely defined traces, and on the Patterson idea, and the sigma A is the scale. That is, you take a strict positive element, you look at the dimension function, which is the same as just what I wrote there. And there is a generalization of this. It says, if A and B be two separable, simple, amenable, C-stable C-star algebra in the UCT class, assuming pairing are trivial, then A is isomorphic to B if and only if the Elliott invariant are the same. We omit certain things which don't really matter here, but doesn't mean they do not exist. It's simply say pairing is zero. Okay, so let me explain a little bit more. So from this classification result, you know there is a unique W. That W is the one with the unique tracial states in the class, and you're absorbing, self-absorbing. And Z0 now can be written as, this is the unique separable amenable simple C-star algebra with a finite nuclear dimension in the UCT class with this K-theory. And moreover, you take any separable simple amenable C-star algebra A in UCT class, A tensor Z0 in the class that is classified by the previous theorem. So that there is a large class there, and they hit all the possible invariant. But that's not quite the end of the story. The world is far from perfect. There are separable stably projectionless Symposius algebra such that the positive cone is 0, the pairing is not 0. I will give you an example later. But what is the pairing? Well, if you have a tracial state space, the one may just define the usual way as a pairing. But it doesn't really work in general, right? You have a stable C-star algebra, tracial state space is empty. There is no trace. So you should really consider densely defined trace. But A may not have any projection. So you really need to consider a tilde instead. But if you have a stable C-star algebra and it's a stable projectionless, you have to consider projection outside A, so A tilde, then all the traces zero, infinite. You look at the difference, is still, well, it doesn't make sense. So you cannot really define that way. One way to do it is you take a positive element in the Peterson idea and you cut down B, then you have a Hilbert subalgebra. And it's stably isomorphic to A if A is sigma unital. One can define a pairing on K0B. Since the K theories are isomorphic, but the problem is that this is not quite independent of B. You give a different B, what are you pairing? Pairing value changed. So let's see, if you have a C-star algebra, assume you have some non-zero trace. If the trace is bounded, then you nicely extend it to A tilde. Let's call this is a set of bounded trace. Then you can define a similar way to a pairing. It turns out that it is a continuous affine function. In particular, in the case, if everything is bounded, then nothing's changed. So what we do is we take a strict positive element, we cut the tail, you get a sequence of elements which form approximate identity. Each En is in the Peterson ideal. So you can cut down An, and then you can have an embedding from An to N plus 1 and so on, and you can extend unitary. Let me just quickly say that you will have a inverse limit of these traces. And from there, you can define a diagram. And this is actually a commute diagram. So that will allow you to have a pairing. Now its value was determined. Of course, that you have to really work out to show this is independent of choice of the strict positive element. And it turns out you can do that, not too hard. And moreover, when A is simple and algebraic simple, it's not really new. It's just the same old thing. And this is actually nice defined pairing, and it has functorial properties like that. But let me say that we actually need something else, and this is a result with George Eliot, Gong, and New. It says if A is a non-unital separable, stably projectionless exact simple C-star algebra, which is Z-stable, and it has a non-zero trace, then that you can find at least one trace that the pairing at that point is 0. Now, let me say this is actually very important theorem. It's actually sort of foundation for the classification of a non-simple case. is about this restate this theorem. Says if A is separable exact simple Z-stable C-star algebra, if you have element, actually the pairing give you strict positive, then it is actually come from a projection. This is what George called the strong version of a weakly imperforated. So this allowed you to omit the positive cone, because this is actually tell you what is a positive. And this deluded us for a very long time. This is only proof like in 2017, even though it's predicted by George Eliot for a long time. So with this, we can see the classification of those algebra that with a positive pairing and to the unital case. So these all reduce to the unital case. But it turns out even this strong version of weakly imperforable pairing needs to be even stronger. So we actually have this statement. That is not only you have a, for any element you have some zero somewhere, you have a common zero on the trace. And this is really what we needed in the end. All right, with all these restrictions, or I call the description of invariance somehow, we'll state a little bit later. And we can talk about the invariant. So a simple order group pairing is a triple. So G is any countable abelian group. T is a convex topological cone with a metrizable Short-Wave simplex as its base, and a homomorphism row from G to the real continuous affine functions on T. And if it automatically gives you a positive cone, if G positive is not zero, then it is a simple ordered group. It's always weakening, unperforated. A scaled simple ordered group pairing is a quintuple. So you will have additional things. So GT low is a simple ordered group pairing, and S is a lower semi-continuous function, strict positive. And there is a scale in the group part. Either it's everything is smaller than S, or there is a U. So low U of S. And we certainly allow the sigma G is zero, if you somehow wondering. It is called unital scale simple ordered group pairing if it is the second case, in which case U is called the unit of G. And in this case, U is the maximum element in sigma G. The warning is that even though sigma G may have a maximum element, it may not be unital. Okay, so this is our invariant. Eliot invariant is a simple order group pairing together with another countable abelian group. Let me quickly move to this slide. It simply means what's a homomorphism among our pairings. Then you need all the map, somehow the group is, the maps compatible. So there is a commuter diagram. And isomorphism, of course, means group are isomorphism, cones are homeomorphic. Okay. All right, so now we are ready to state the first theorem. It said, let A be a separable exact simple Z-stable C-star algebra, then its Eliot invariant is indeed a simple scaled ordered group pairing together with a countable abelian group. Well, what that means is to say this K0, maybe I should show whole scale slice. So this sigma K0 are the image of projections in the K0 in A. And sigma A is a lower semi-continuous function. It's a scale. And rho is a pairing. And Elliott invariant is this six tuple. Okay, so there's a simple order group pairing and together with the K1 of A. So this is, we call the description of the invariant. And it's a theorem. If you think that's, it's just a definition. All right. So the main point, maybe I should have mentioned that you have to work with in the A tilde instead of A, and in order to get a K0. And A tilde is not C-stable, nor it's approximately divisible. So that's one of the difficulties there. Now I'm going to give some example, even in the not stable projectionless. Let's say you have Jiangsu algebra, you take element with the trace 1, which is not projection, and you cut it down, you get a non-unital Symposius algebra, and the Elliott invariant is this six tuple. So you have a group Z, unique trace, and this scale of a group is 0, and K1 is 0. And the pairing is the usual one. And this is not a unital algebra. So you need that thing to distinguish them. And let me give you another example. You go to the 3x3 matrix, you take a non-projection element, and you cut down that B. And now, in both cases, this scale G has a maximum element. This is just 0. If you don't like that, you look at this one. It has true maximum element, but it is not a unit. It's not a unital algebra. So you need this portion to describe, to distinguish unital, non-unital, and the scale. Okay. All right. So let me quickly say this. This is the range theorem. So you say you're given any scale simple ordered group and any G1 as a countable abelian group, then there is a simple separable amenable C-star algebra satisfy the UCT. So the Elliott invariant is precisely this simple ordered group pairing together with G1. You can't tell unital from non-unital. So A is a unital if and only if this sigma G0 has a unit. If it has some positive pairing, then A can be chosen to have a rationally tracial or generalized tracial rank at most 1 and an inductive limit of subhomogeneous C-star algebra. If there's nothing positive, then it's A can be chosen, construct as a stably projectionless, and have generalized tracial rank at most 1, and it's locally approximated by subhomogeneous with dimension no more than 3. In case G1 is 0, G0 torsion-free, then A can be chosen to be an inductive limit of one-dimensional non-commutative CW complex, that's what they call it. So this is the range theorem. But with this range theory, I want to say a couple of examples. So Z0 is actually inductive limit of one-dimensional NCCW, if you remember what Z0 is. But then you can produce, we call Z1 negative 1. That is the K theory as a group, still Z. But the pairing, there are two traces. One has a value 1, the other is negative 1. And positive cone is 0. But if you think that is easier, this is the last example really bothers us. That is, can you have a non-negative pairing? That is, can you have a simple C-star algebra? So the the image of this pairing of K-theory is actually non-negative, but not quite a strict positive. And it turns out we can produce any of those. And just to let you know, you can have C10. So you have the same K-theory as a Jiangsu algebra, as a abelian group, but you have two traces. One trace is 1, the other trace is 0. And that's actually possible. And also, well, I want to really mention is if it's unital, separable simple Z-stable algebra has stable rank 1. We don't know in general that's true for non-separable ones. Nevertheless, we all have these things, things you expect to be true. And then there is a reduction theorem. That is, if you start with a separable stably projectionless simple amenable Z-stable C-stable algebra in the UCT class, then it has generalized tracial rank 1 and it has stable rank 1 in this case. So we need to use, if we don't know in general it's true, okay, in this case. So this is the what we call the reduction theorem. So you have a range description, and then you a description of the Elliott invariant and the range theorem, and together with a reduction. And we first prove the isomorphism with this additional condition. This is really help us do the tracial thing. That is, Chris mentioned this tracial extension. So we want to have a tracial condition, but that's automatic in this case, under this condition. And with that, one can describe a unified description of a finite separable simple Z-style algebra. So if you have two unit or non-unit separable simple amenable Z-style algebra in the UCT class, assume it's a finite, then A is isomorphic if and only if the Elliott invariant are the same. And again, the Elliott invariant in this case means that. So in the unital case, unit itself is part of invariant. With the unit, then you don't need this part. If you don't know, you want to Elliott invariant is a really good invariant. It can distinguish itself. Invariant itself can distinguish the unital case from non-unital case. So you can just use this 6 tuple. Of course, it's not really new. It's already predicted by Elliott, and so that's just we just refine it. So this is the isomorphism theorem. So we have a description of invariant. So basically give you restriction, and then you have range theorem, and then they have isomorphism theorem. I think I will stop here.